Hello everybody, I apologize for this, I really do. You know I absolutely hate missing days, but my child came down with a fever towards the end of the school day, and Texas law says that you can't take your child back for 24 hours after they've had a fever. So even though his fever hasn't happened the entire time he's been home, I am not able to be here. With that said, the good news is that this is a nice, lovely, simple topic that I think you'll all enjoy. This is antiderivatives. We are officially to the point where all of that Riemann sum junk that we've done, while is still useful and we still will utilize it in situations like tables, we're not going to ever just take a function and be like, let's do a left Riemann sum of this random equation and come up with the intervals ourselves and plug in the f values ourselves. We're not going to do that. It's a waste of our time. And I hate wasting our time. It would be terrible, horrible stuff. All that definite integral stuff was really good on building the concept of what is an integral and dealing with the area. But integrals are, and we saw that integrals and derivatives also have another relationship that fell out from that study of area. And that was that derivatives and integrals are inverses of each other. They undo each other. So if I take a derivative and then take an integral, I should be back to where I started. Cool. This is neat. That means that there should be some sort of cool operation that undoes it. And in fact, you can probably do them in your head right now. If I were to ask you to take f prime of x equals 3x squared and asked you what function would become the, would have f of x would have that derivative, the vast majority of you would tell me that it is x to the third. You know the derivative of x to the third is 3x squared. You've done that over and over and over. Well, we say that that f of x is called the, not the original function of f prime of x anymore, but we will call that the antiderivative of f of x. Now, a couple things. We say that the expression of the integral of g of x dx, notice that this is weird. There are no limits. This is no longer going to be called an integral or a definite integral. This is now called an indefinite integral, which is one of three specific integrals that we're going to look at. This is the indefinite integral of g of x with respect to x. Holy moly, that's a lot. Now that's the whole thing, the indefinite integral of g of x with respect to x. Typically in this case, we're going to drop the word indefinite. And just realize that indefinite integral and antiderivative are synonymous with each other. They are the same exact thing. They mean the same thing. Those are synonyms, right? I sure hope so. As long as they're not synonyms. Anyways, we can get formulas for antiderivatives by simply reversing differentiation rules. What I mean by that is that if I take a derivative, remember what happened. If I took the derivative of 3x squared, or sorry, not 3x squared, holy moly, that's what I want to get to eventually. If I took the derivative x to the third, we would take the power and multiply it in front, so this would become a 3, and we would reduce the power by 1, right? So step 1, multiply. Step 2, reduce. Well, over here, in the one that's connected to it, if I have 3x to the second and I want to figure out what the f of x was there, what I'm going to do is I'm going to do the reverse. I am going to, step 1, raise the power by 1, and then step 2 is going to be divide by the power. Now that's not hard when we're dealing with x to the 3x squared, and we know what the derivative, and what the antiderivative to that is, but when we get to more difficult problems, that will be important. You can see the derivative of sine is cosine. So if I take the antiderivative of cosine, we just ask, hey, the derivative of what gave me cosine? It's sine. You'll see the derivative of cosine gave me negative sine. The derivative of sine gives me negative cosine. Now that can get confusing because you'll notice the derivative of cosine is the negative sine, but the antiderivative of sine is the negative cosine. They look weird. So what I want to bring up is there's a relationship between these three. And it works a little something like this. This is lovingly called Santa Claus by, I think it was Nick who came up with this. Specifically, for those of you who are fans of Christmas time, since this is so lovingly timed, it's called Santa Claus because, of course, the first The Santa Claus movie was a positive clause. The second The Santa Claus movie had the negative. So if you ever need to work through that. But what I want to point out is that if we think about derivatives and integrals in terms of powers, derivatives take the powers and move them down. So the derivative of sine is cosine. The derivative of cosine is negative sine. And the derivative of negative sine is negative cosine. Well, if derivatives go down, and derivatives and integrals are inverses, then integrals must climb up the ladder, or raise the power. So negative cosine becomes negative sine. The antiderivative of negative sine is positive cosine. And the antiderivative of cosine is sine. And when we get to the bottom or the top, depending on which side we're on, this just loops back around, or this just loops back around. And we get all sorts of crazy arrows. It's great. The same thing happens for tangent, cotangent, and secant. When we look, we're looking for, hey, the secant squared. I know there's a, wait, that was the derivative of something. Another couple important pieces of information. Just like definite integrals, we can add and subtract individual pieces. So just like derivatives, we can split that. I can factor out constants, which will be a huge benefit for us later on. And I want to note that there is no cross multiplication and a cross division, just because at this point you should realize if those two things are related, derivatives and antiderivatives, that same rules will apply. So real quick, I'll do the first couple, and then I'll give you a shot on the next ones. If I wanted to take the antiderivative of x to the fifth dx, I would take the fifth power and raise it by 1 over 6. Oh my goodness, I forgot one of the most important parts, and a plus c. I didn't mention this, so let me go back real quick. I apologize. You'll notice that there is something very strange on all of these on the right. You probably were wondering that for a while, hoping that I would talk about it. That every single one of these has a plus c. And you might be asking, where on earth did the plus c come from? And the answer is pretty good, actually. You're going to enjoy this. When I did that antiderivative of the very first question, I'm sure that the vast majority of you went x to the third. But couldn't it have also have been x to the third minus 2? Or could it have been x to the third plus 17? Or even x to the third minus 2.37 times 10 to the 15th power. See, remember that if I take a derivative of a constant, that constant disappears. So if I wanted to take the antiderivative, there may have been a constant that fell out when we took its derivative. So that plus c is accounting for the fact that, hey, there might be a constant. What is a constant? We don't know. But we'll find out. So that plus c actually turns out to be incredibly important. In fact, it is so important that if you forget to put a plus c at the end of an indefinite integral, you are absolutely wrong, and you will get that question marked wrong, guaranteed, no questions asked. If I sit down and give you a formative about this and you don't put a plus c, just like if you don't put a dx at the end of an integral, it's wrong. The c is major. It's not minor. So my music people get the joke. Anyways, moving on. If I take a look here, if we integrate, oh, don't do this to me, computer. Oh my goodness. If we integrate this problem just like with derivatives, come on, here we go. With the derivative, we would rewrite that. We would do the same thing here. So we would say that this is the integral of x to the negative 3 dx. We would raise the power by 1, so x to the negative 3 would become x to the negative 2. Divide that by negative 2. And we would add c. So I'm going to give you all a few seconds to try these questions out. If you would pause this and try the next 4 out, see what you can come up with. All right. So after you've paused this, so you can see that we have several answers here. The ones that probably were the simplest are going to be these bottom trig ones where we go, okay, the derivative of what would give me sine. That's one that I would highly think about using this right here and going, well, the antiderivative of sine. So if I were to do that, sine would have to go, sorry, I did cosine of sine, but sine would have to come all the way around to get to negative cosine. Looks kind of like an ear. Or for secant squared, going the derivative of what is secant squared. This one wasn't too bad. If there's one that I would be a little more interested in, it would be this one right here. Remember, if I add 1 to 1/2, that's 3/2. So you get x to the 3/2 over 3/2. I will never leave it written like that. It's too confusing for me. And that's not how they're going to write it on multiple choice. They're always going to take that, divide by 3/2, and turn it into multiply by 2/3. All right. Just to make a point, there is no product or quotient rule, so you're going to have to do some simplification. In fact, there is literally no product and quotient rule. You might be happy about that for now. It'll come back. Not a product or a quotient rule, worse. So what I can do is I can multiply this out. I can call this 2x cubed plus 6x minus x minus 3 dx. I would obviously simplify this because, I don't know, I don't like to do more work than I have to. Technically, I should have parentheses around those. So if I do that, I take the antiderivative of 2x to the third, which will be 2x to the fourth over 4 plus 5x squared over 2 minus 3x plus c. And then to simplify, and I would move on there. Likewise, in this problem, I would recognize that this can actually be split. You know what? I'm going to do that a slightly different way. Come on, computer. As I take a look at this, I can realize that this is really rewritten as 1 over x squared times the numerator. And the reason why that's useful is I can distribute this across and call this x to the third minus 5x plus 7x to the negative 2 dx. And if we do that, we take the antiderivative. That becomes x to the fourth over 4 minus 5x squared over 2. This is a fun one. This becomes plus 7x cubed over negative, not cubed. 7x to the negative 1 over negative 1 plus c. Again, don't forget that plus c, the stinking plus c. So this is 1/4 x to the fourth minus 5/2 x squared minus 7x to the negative 1 plus c. And that 7x to the negative 1 can be 1 over that. Sadly, I'm running out of time for my video when it comes to how much time I could be in the building. So I'm going to try to get through this as efficiently as possible. If I don't manage to get far enough through all of the notes, I believe you have an assignment where you're not necessarily finding differential equations. I do want you to try out some of these. What I want you to realize is that I've talked about this before, but differential equations are really anything that has a derivative in it. So if it has an f prime, f double prime, dy dx, second derivative, anything like that. A differential equation is just an equation that has a derivative. And we can actually solve that. If I have an f prime, I can go up to f by taking an antiderivative. And when we first integrate the question, remember we get that plus c. That's a general solution. So what that means is this. If I take f prime of x is equal to 6x squared, I want to find f of x, I simply say, well, this becomes the integral of 6x squared dx, which is 6x to the third over 3. By the way, if you know what that's going to reduce to, if you know that's going to become 2x cubed plus c, you can go ahead and do that. This is called a general solution. Because technically that constant, by the way, the whole thing is the general solution. Technically that constant can be whatever I want. Positive, negative. There's an infinite number of solutions that could be fit there. But you'll notice that I give you a little more information as well. I tell you the f of 1 is negative 3. What that means is there's a specific point I want you to go through. And if a function, oftentimes what will happen is that there will be sometimes where there will be multiple c's that might work, but most of the time there is a specific c that will cause this general solution to become a very specific solution. So what I mean by that is that we can say, well, the f of 1, which I know is going to be 2 times 1 cubed plus c, is going to equal negative 3. And I can solve for c. This is 2 plus c is negative 3. C is negative 5. And once I know what that c value is, I can substitute that back in and say, well, then f of x is going to be 2x cubed minus 5. And this is called a particular or specific solution. So, other things that could happen on occasion. I could give you a situation where it's a second derivative and I want you to solve the differential equation. What that means is that I want no f primes or f double primes or anything like that. So to get rid of an f double prime, we would have to take an antiderivative. F double prime, to get to f prime of x, we would have to take the antiderivative of the cosine of x with respect to x, which in this case, if we do this, is the sine of x plus c. Another way to think about this, just like how I say on a cosine function, the slope goes down. Well, if I look between 0 and pi, the area is also going to turn out to be positive, although that's going to be true for cosine too. So just kind of go with it at this point in time. I'm trying to think if there's a way to do that. I had come up with one. Now this is again our general. We want a specific. So they tell me originally that f prime of 0, so we want f prime of 0. Okay, that's my sine of 0 plus c, and that should equal 3. Well, the sine of 0 is 0, so c is 3. So f prime of x is really the sine of x plus 3. Now that's my f prime specific solution, but it is not my solved differential equation because I have not found f of x, which will be the integral of the sine of x plus 3. You'll notice I keep putting parentheses around my argument. Some people do that. Most people, you should do that. It signifies that the entire derivative goes, or the entire function is inside of my integration. Although if you're very specific about your integral in your dx, they sometimes will be very kind to you. But the parentheses are useful and should happen, so please do so. If I take the antiderivative of this, the antiderivative of sine goes to negative cosine. This becomes 3x, and we get a plus c. So that's my general solution. I have an infinite number of solutions that fits here, but I know that f of 0, which is the negative cosine of 0 plus 3 times 0 plus c, is going to be negative 2. So the negative cosine of 0 is negative 1, plus c is negative 2. c is negative 1. Therefore, the f of x in this problem is the negative cosine of x plus 3x minus 1. Sadly, I'm running out of time, so I will not be able to look at this very last question. I hope you all have a fantastic day. Again, try out some of those homework questions that is inside your tracker so that you can get a chance to practice this and do what you need to be successful there. I really look forward to seeing you all tomorrow, folks. I'm really hoping that everything is good to go. I do have your formatives from last week finished. I just forgot to give them to you yesterday. I'm working on your test today. They should be in the book by this evening. And I hope you have a good rest of your day. Thank you so much.